I want to talk a little bit about the relationship between pH and the hydrogen ion concentration. So in dilute solutions, we can approximate the pH or define the pH as the negative log base 10 of the hydrogen ion concentration. We'll represent the hydrogen ions as H plus and their concentration with little brackets around the H plus. All right, this equation leads to a relationship between the hydrogen ion concentration and the pH that a lot of students find confusing. And that is that there's an inverse relationship between them. When the pH goes up, the hydrogen ion concentration goes down, and when the pH goes down, the hydrogen ion concentration goes up. So I thought we'd explore that a little bit to see if we can get a little more intuitive sense of how that works. So let's start by making a table. All right, and on this table we're going to represent the hydrogen ion concentration in a couple different ways. So we'll start with the hydrogen ion concentration in this column. And then we're going to represent the hydrogen ion concentration, same number, but as a fraction. And then we're going to represent it yet again in exponential form. And then we're going to take the log base 10 of the hydrogen ion concentration. Finally, we'll take the negative of that, which is going to give us the pH. Okay, so let's start by writing a few concentrations, and all these concentrations are represented in molar units. So we'll start with a concentration of 0.1 molar hydrogen ion concentration. We can rewrite that as a fraction. That's 1 over 10. We can rewrite that in exponential notation, so that's 1 times 10 to the negative 1. Great. Let's do another one. 0.01. All right, we can write that as a fraction. 1 over 100. And we can then write that in exponential form. So that's 1 times 10 to the negative 2 molar. You can see where this is going. 0.001. That's 1 over 1,000, or 1 times 10 to the negative 3. All right, we won't write too many of these. We'll just skip down a few and write maybe 0.1. I'm not going to write out the fraction. Too lazy to do that right now. We'll just say that that equals 1 times 10 to the negative 7 molar. Let's do one more. 0.000000001. 1 times 10 to the negative 8 molar. All right, so let's start by looking at this for a second. What have I done? I've written a series of concentrations in this first column, and I've started with a high concentration or higher concentration, and then I've progressively gone by a factor of 10 to smaller concentrations. So as I go from the top of the column to the bottom of the column, right, these numbers are getting smaller. That means that these numbers here in the exponential form are also getting smaller as we go from the top to the bottom. All right, now let's take the log base 10 of this number, right? And that's relatively easy. We just grab the exponent on this number here. And so the log base 10 of the proton concentration for the first row is negative 1. For the second row, it's negative 2. For the third row, negative 3. And so on. And down here, this is negative 7 and negative 8. Now, what we did was calculate this piece of the pH equation, we need to take the negative of that number to get the pH of that concentration. And so if we take the negative of -1, we end up with 1. The negative of -2, we end up with 2. Negative of -3, 3. And we can go on, 7 and 8. All right, so now let's look at the table. Recall, as the hydrogen ion concentration here on the left, as we went down the table, those numbers decreased. That was evident whether we wrote it as a fraction or an exponential form. And then when we calculated the pH, those numbers increased as the concentration decreased. All right, so that's the relationship between the concentration of protons and the pH, and why we have an inverse relationship between the two. Hopefully that helps and clears up some of the confusion.